Now we're going to do the Verilog, and I am actually not going to do this in Vivado. You can if you want, but I'm just going to write it out instead. Because I think maybe well, no, I'll do it in Vivado. Yeah, I'll do it in Vivado. Except maybe you can't see that. Is that too small? Well, wait. I'll write it out. Okay, so you have to keep in mind the machine that we just did, because our code is going to be based on that. Okay, so first I'll give it a name. So module finite state machine. And what I'm going to have, I'll have some inputs. So I'm going to write input. My first input is going to be my clock. And then I'm going to have an input I'm going to call L. And what this input L is going to be used for is going to be for testing. So if I want to load a particular state into my finite state machine, then I'll have L equal to 1. And if I want it just to run on its own, just to like keep going, next state, next state, next state, L will be equal to 0. So L is going to be my input, and this is the same as what your lab is tomorrow. L is my input that tells me whether I'm loading the next state, by putting in the variables, or if I am just getting the next state naturally. And then I have an input. This machine just has one input X. We have just one output Z, except we're going to define it inside an always block. So we need to have output reg Z. And we're going to have our present state, and our present state for the one we have is 2 bits. So output reg, and we had Q2 and Q1, so just to keep it the same as what our equations were, I'll do 2:1, and I'll call that present state. It's kind of weird, we call it present state, but it's actually when we compute it, it's the next state. But when we output it, it becomes the present state. So what that means is when we compute it, we have the next state, but that's not an input or an output, that's something we're computing, and we're going to compute it in our always block. And so that'll be reg 2:1 next state. Yeah, so I did a shortcut here compared to what I normally do. Normally I list all my variables in the parentheses and then I list them out as input or output. You can do it all in one step, but something that's not an input or an output is outside those parentheses. So the other way I could have done this is like this.
You don't have to, it's not a wire still? Even though it's
That's a good question. Is it a wire in y'all's code? In the lab tomorrow? Yeah.
It doesn't say input or output though.
Yeah, so it's not input or output.
Yeah, it just says reg.
It's not a wire because it's not actually connecting two things. So I don't know. I hadn't thought about it, but yeah, it's not. It's just just reg. Okay. Then, because it's a lot easier to use the letters than it is to use the binary numbers, we define our states as parameters, and so we can just use the letters instead of the numbers. So we just say parameter, and ours were 2 bits, so 2:1. And I will have A equals the 2-bit, so that's 2 apostrophe B binary 00, comma, B equals 2 apostrophe B 01, comma, C equals 2 apostrophe B 10, comma, and D equals 2 apostrophe B 11, comma. And actually the last one's not a comma, the last one's a semicolon. Okay, so now I'm going to compute my next state. So I don't actually change it yet, I'm just computing it. So I'll have an always block, and my always block, I want it to compute the next state anytime I get a new input, so X, or when I have a new present state. Because if you remember, our values were all based on X and our Q's. So whenever those change, we need to go into this always block. Now we could, if we wanted to, have a case statement that was based on a 3-bit binary number with X and also the present state making up a 3-bit binary number, but I'm going to do it just based on the state, because for me, with a finite state machine, the whole point is looking at what the different states do. And so your case statement will be listing out your states. And so that's what that's what I would do here anyway. Okay, so we're going to start with, let's say we're in state A. So A colon, and then begin. So if we're in state A, this is a Moore machine, and so our output, we don't have to worry about what X is, we can just right away say what our output is. And for state A, if you recall, our output was 0. And our next state was A if X was 0, and it was C. Or was it W? Was W our variable? W was our variable. Okay, I'm just using X here instead of W. So it was that if X is 0, our next state was A, and if X was 1, our next state was C. So we start by saying Z equals 0, and then if X equals 0, then our next state, and here we'll use a non-blocking assignment, our next state is A, else our next state is C. Okay, so I'm going to do B, and then y'all are going to do C and D on your own. So B, we'll have begin. So let's look at our state table. For B, our output is 1. If X is 0, our next state is A. And if X is 1, our next state is B. So our output was 1. And if X equals 0, our next state is A, else our next state is B. Okay, so y'all do C and D now, and then we'll check it after you've had a chance to try it for a little bit. Okay, so let's see how y'all did. So for C, we'll have begin, and then what's next? Z equals 0. And then if x equals 0, next state is A, else next state is B, I think, right? Yes, it's still B. And then I think I forgot my ends on all of these, yeah. So for A, where I have begin, I should have had an end. And for B, I need an end. For each case, whenever you have a begin, you need to have an end. And so all of these should have also been indented because you want to keep your code nice and neat. Okay, and then D, begin, and that would be Z equals 1. And if x equals 0, next state is A, else next state is B. Okay, now we have it's 2 binary numbers, which means there are 4 possibilities, and we have options for all 4 of them. So officially, we don't need a default. If we were missing one of these states, we definitely want to put a default in. But it's always a good idea to put a default anyway, in case you come in and you change something later on. So we're going to put a default in, just to be safe and for good practice. And so we'll have a default. But definitely, if we were missing a state, we would want to put one in. So default. Oh, I forgot my end. So D needs an end. So default begin. And I will let Z equal, it's a binary digit it's 1 binary digit, so it's 1, B, and then I put a lowercase x, and that stands for don't care. So Z is a 1-bit don't care. And next state is a 2-bit don't care. So 2 apostrophe B X X semicolon. And I don't care what X is because, well, this is different X. This X is a don't care X. But I don't care what my input is because it's all don't care. And then this is end.
So that's it. Your state that you get to, like it just like resets it, to like a certain state.
You don't know what it could be. It could be anything. Yeah.
I have a question.
Yes.
So for our, I see how our Z values change, but what about our X values? How come it says 0 throughout the whole thing?
Well, it's an if statement, so it's not 0 throughout the whole thing. It's saying if x is 0, do this,
Okay.
and the else is when x is 1.
Okay.
Yeah, I don't actually know what Verilog or the basis board would do with that.
So I know on the Verilog, it doesn't. It's because it's the state is a 3-bit number, and it doesn't have one. Doesn't have a state for when it's all 1.
Mm-hmm.
1, 1, 1.
Right.
So there's a false thing, and it does get don't care.
Mm-hmm. So what you're saying is that when you don't have that state, you're saying that you don't ever expect that state to show up. So you're not ever expecting it to be 1, 1, 1. But if it does, you need to be able to deal with it, and you're not prepared for it because you're not ever expecting it to happen. So it's just going to be something. You don't know what it is.
So couldn't it do all ones again? Because if it's a don't care.
You mean couldn't you say make it 1, 1, 1?
Or like if it's a don't care value, couldn't it until you get that state, and then couldn't it just stay in that state? Because if it's a don't care value, then
Yes,
be
it could.
1.
It could. Yeah. Okay, and then now I need to end my case statement. And I will end my always block. Did I begin my always block? I didn't, because the only thing in my always block was a single case statement, and I forgot to put my case statement in there. So I should have put up here at the start of my always block, case, open parentheses, present state. Because I'm checking my present state to figure out what to do. So that's my case statement. So I left that out. I also, while I'm here, I left out an input that I need. And what this input is remember I told you we're going to use L as kind of our test to say if L is 1, you're just going to load a particular value to see what happens. Well, what value am I going to load? Well, I'm going to put, this was not part of our state diagram. This is part of just Verilog. So this is testing. So I need to have an input that's going to be what I'm going to load. And so my input, so this is just goes in here, input, and I'll call it S because that's what y'all are calling it in your lab. So input 2:1 S semicolon.
So let's just put a test bench so that when L is 1, that's the state that's loaded.
Yeah, it's not just for the test bench. So when you actually load it, and so we'll get to this when we do the constraints, you're going to have a switch for L, and when L is 1, you'll have 2 other switches that you'll put in for present state. So you're saying, okay, I want to see what happens when my state is 0, 0. And then you press the clock button, and then you see what happens. So it's for the test bench as well.
Okay.
So the test bench, but if we didn't have, if it weren't for wanting to load S, we could have left S out and just had our test bench go through present state. Our different values at present state. Is that?
Yeah, because on the test bench on the physics lab,
Mm-hmm.
there's a part where it goes through a for loop.
We're gonna get to that.
Okay.
If that's okay, or I can.
It's S equal to like the value that's going to the for loop.
Yeah.
So that's what you mean when it's the state that is, when you check the state, that's what that is, like on the board.
Yeah, so on the board, so what S is on the board, if I want to see, I want to put myself in state C and check and make sure the right thing happens when I'm in state C. Then what I do is I flip the switch for L to say I'm loading a state, and then I flip the switches that correspond to state C, and then I load that. And then what the test bench does is the test bench just loads all possibilities so that you can see what happens with all of the possibilities. The test bench does it automatically, all the possibilities. If you're using the board, you have to do it yourself one by one.
So how's that different from present state?
You can't control present state. So, well, we haven't actually said where present state comes from yet. So, and that's going to be, because right now, we just have at present state, but present state is not an input. It's actually an output. And so we don't really know where it's coming from yet. But you don't control present state. That's controlled by the code and the board. So if you want to control it, you have to load it. So that's where, so what we've done now is this always block has computed what the next state will be and the output is, but it hasn't actually changed it yet. That happens with another always block. And you always are going to have two always blocks with finite state machines. And your second always block is always at positive edge clock. Now it doesn't have to be at the positive edge of the clock. It could be at the negative edge of the clock. But this is when you're changing states. So this is when you're saying, okay, flip-flops, do your thing. Okay, and this is where you're going to check. Am I just going to let my finite state machine run and come up with its next state based on the state diagram? So if my finite state machine just runs, it's just going to go to the next state, and then the next state, and the next state. It might get stuck in one state and stay there, depending on the machine. And so, or am I going to interrupt it and say, I want to load a state? And that's what this is for. And so here, I'm going to say if L equals 1, then I'm going to make my present state equal to S. So this is saying I'm loading a particular state. Else, I want my present state to be this next state that I just spent that whole always block computing. And this always block is usually going to be very, very short. You're just going to have, you're just loading. This is just where you're saying it's time to advance the clock. And that's the end of your source module.
Rebecca, I have a question.
Yes.
So I think it was something from last lab, and it said like, could we rewrite this in the way that we have the two always blocks merged together?
Are you asking could
like,
we
of
put?
course it would.
Are you asking could we put these always blocks together?
Yes.
Okay, the answer to that one is no, and that's because of the nature of the finite state machine. We want this always block. It's not doing the calculations. The bottom always block, all that's doing is saying advance to the next state. And you don't want to be doing that at the same time as you're calculating what the next state is. So because if you did that, everything would get all confused because your next states wouldn't necessarily all be in the right place. And so you need to make sure that those are separate.
All right, gotcha.
Okay. All right. So now I'm going to look at the constraints, and then we'll look at the test bench. For the constraints, I'm just going to load my file because it won't be useful for you to like copy. These you can get from the template that Vedi has given to you. So there's a couple things here. First, I don't have my Windows set. Oh, yeah, actually, you can see it. So the first set property that you're going to have is one that he has on his lab instructions, and it's new. And I'm going to stop the share for a minute, so stop the screen share so I can show y'all something on the camera. Okay, let me turn on my camera. Okay, so you're going to have something new in this lab, and that is this little button. So these are, you have these right here. Jaden? Right there. These are going to plug into your board. I think it says on the top. So it's going to plug into your board. This is the top left. My screen's mirrored, so it looks like the top right, I think. But and it's this port has 2 banks in it, and you're going to plug it into the top one. And what that code does is it makes it so that the bottom right button, which is button 0, is the clock. And it's a debounced switch, and what that means is that it just works better. You don't have to worry about, like, you know, is it when I'm pressing down or when I'm pressing up. It's just going to work nicer than the switches that are actually on the board. So that's what that is for. And that code is just right on your lab, so you'll have that. Okay, and then you're going to set some switches, and so you can set whatever switches you want. So in my example here, my state only had 2 numbers in it, so I only have S1 and S2. You're going to need to have S1, S2, and S3 because your state's going to have 3 values. So you're going to have 3 switches for S1, S2, and S3. And you have 2 inputs. So you're also going to have a switch for, I don't remember what your inputs are, but I think you have 2 of them.
Yeah,
X and Y. So you have two switches, so you'll have both of those. And you have L. And it's the L that tells you on the next clock cycle, when I press that button, am I going to load the state that I just set with the S switches? Or am I going to let the finite state machine decide what its next state is on its own? If L is 0, then the S switches aren't doing anything. You can do them however you want. They're irrelevant. Because when L is 0, the finite state machine is just going to go to its next state. When L is 1, it's going to get its state from those switches. Okay, then you're also going to have some LEDs, and you'll have your LEDs will display your present state. So on mine, I just have the 2 here because I just had the 2 values. You're going to have 3. He did say that he wanted your most significant bit to be on the left. So if you have these in your order that he has them in the template file, then you'd have them in order of 1, 2, 3, and then that would put 3 on the left because U16 is the furthest on the right. And then you will also have 2 LEDs that correspond to your output. Do you have 2 outputs?
I think it's just 1.
Just 1? Okay. Well, you'll have an LED corresponding to your output. Okay, so any questions on your constraints? Actually, the constraints is where I usually get most of my errors. When I go to compile, it's almost always that I've messed up a closed brace in one of these, or I have the wrong value in one of these. So when you get an error, check your constraints. That's almost always where I have my mistakes. Because you see your mistakes in your code while you're typing. You'll get the little red squiggle that's saying you've got an error here. You won't catch a logic error, but you'll catch other errors. Okay, so now I'm going to go to the test bench, but before I do that, are there any questions?
Did you use from the template the clock signal?
No, the clock signal came from this particular lab because the clock signal is now going to correspond to these buttons. So it's just there for you to directly copy from this lab. Okay. So I am not going to have time to do a more complicated example, obviously. So, well, not obviously, but yeah, I'm going to be done after I do the test bench. But I will record a more complicated example for y'all to look at before your homework is due on Thursday. But I'm not done yet, Jaden. I know you hear me saying that, yeah, but I'm not done. We still have to do the test bench. But you can go if you want. I'm not yet.
Yeah, it's fine.
Okay. All right, so here's your test bench. So let's talk about what we'd want to have here. So module, FSM, and there were questions on the test bench for your pre-lab. So you do want to make sure that you take a look at that you are supposed to answer those questions as well. So with your test bench, your inputs are reg and your outputs are wires. So we will have reg, clock, L, X. I'll have reg 2, 1, S. And I have a wire is Z. And I have a wire is 2, 1 present state. And I have some for loops. And when you have a for loop, you have to have an integer for your counter. So I'll have integer I, J for my for loops. Then for a test bench, you have to tell it what you're testing. And so here you put the name of whatever your module was. So let's see, what did I call my module? I called my module FSM. So here's where I tell it that I am doing, this is what I want to test. So FSM, that's the name of my module. And then I put UUT. And then open parentheses. And then if I use this dot notation that I'm about to use, I don't have to worry about whether the order matches the order in my module. So I'm going to put dot CLK and then CLK. So that's one of my variables. Dot L is L. Dot X is X. Dot capital S is capital S. Dot Z is Z. And dot present state is present state. Then I'm going to initialize it. So I give everything initial values. And I'm just going to put a display on the screen to tell myself, or to tell the user that we're starting now. So open quotes, and then the /n is for a new line, and then start, and then /n for a new line, and close quotes. And then I'm going to set everything equal to 0. So I'll make clock equal to 0, L equal to 0, X equal to 0. I'll make S equal to the binary number 0, the 2-bit binary number 0. And then this hashtag 100 is just saying pause for 100 nanoseconds. Okay, then we have 2 nested for loops. And what our nested for loops are doing are to go through all of our possible values of present state, and then also through our 2 possible values of L. No, hold on. No, our 2 possible values of X, not L. We're going to always have L equal to 1 here. For our test bench, we need L to equal 1 because we don't have buttons to press. Since we don't have any buttons to press or switches to set, we need L to be 1 because we need it always to be loading the next state from the S value that we're giving it here. So in our test bench, L is always 1 because we don't have any physical switches to set. But we do have 4 values of present state and 2 values of X. So I will have my outside for loop will be I equals 0, I less than 4, I equals I plus 1. I don't think Verilog does I plus plus. And then I'll begin that for loop. And so that's going to go through my 4 states. So this goes through my 4 states. And then for j equals 0, j less than 2, j equals j plus 1. And that goes through my 2 inputs. And I'll begin. So if you had when I say 2 inputs, it's one input that has 2 values, 0 and 1. So if you have 2 inputs, you'd have 4 values, 0, 0, 0, 1, 1, 0, 1, 1. Now I set L equal to 1. Like I said, L is always going to be equal to 1. And then S, that's the value of my present state that I'm going to load. I'm going to let S equal I. And then I'm going to pause for 3 nanoseconds. And then I'm going to change the value of the clock. And this I'm just copying from what he did. And I'll pause from 3 nanoseconds and change the value of the clock. So this is just advancing the clock.
So when L is equal to 1, that's when we can load the states, right?
Right. And that's what we have to do here, because it's getting the states from S.
But those test benches isn't just going through all these states and checking? So doesn't it not matter? Like, so I wonder why that was 1.
Okay, because we are computing, we're going to output present state. We can't output and input the same thing. And so we have to have a way to run through all the various different values. And with the code the way it is, you don't necessarily get all the values one after the other, because it depends on your finite state machine. Your finite state machine goes from, depending on the input, it's not necessarily going to go to the next state. As a matter of fact, in the one that I have here, if you look, if I start in states A, B, or C, I never get to state D. And so if I want to check what happens with all of my states, I need to load them manually. I need to load state A, then what's the next state? And state B, and then what's the next state? And state C, and then what's the next state? My test bench is not running the finite state machine as the finite state machine. My test bench is testing it. It's saying, I'm giving it state A, what are you going to do? Okay, good, I've got that. Now I'm giving you state B, what are you going to do? When the finite state machine is actually running and you're not testing it, you're not doing that. You're just sitting back and saying, what's the next state, next state, next state, next state. It's doing it on its own based on the previous state. But to test it, you have to tell it what state you want it to be in. Okay.
So that's why we make I here, that's why you're going to make S equal to I.
That's why I'm making S equal to I, because that way I'm getting all my states. So it starts with, in this for loop, it starts with state 0, 0. But I need to check state 0, 0 for input x equal to 0 and input x equal to 1. So I also have x equals j. So now that's my second loop. So for each state, I'm checking each of my values for my input. And then I'm advancing the clock again. and then I'll end my inside loop, and I'll end my outside loop, and then it's always a good idea to display that you're done with your... Oh, now notice something with this test bench. So I'm just copying what he had in his test bench. Notice one thing that I did not display here. I don't have any idea what it's doing. All this does is just run through them. So you would want to put, if you're using this to actually test something, you're going to want to put a display in here. Display. And then I just did, that's okay. So a binary number, and then present state. To see what am I getting? So this test bench doesn't display anything at all. So you probably are going to want to display more than just the present state. You're probably going to want to display S, so you know what state you're in, and X, so you know what your input is, and your present state, so that you know what your next state is. So you're probably going to want to display all of those. So then display, and I'll put ended /n, semicolon, then finish, and then I'm ending, what am I ending? I'm ending my, this begin right here, and then I'll end module. Mm-hmm.
Why'd you put the like that statement in between the clock, those clock statements?
Oh, okay, because I forgot something. I also needed to put... Okay, I said something wrong earlier. Okay, yeah, so here's... I do need... This is what I left out. I do need L to equal 0 right here, because at L equals 0, that's when it actually computes the present state. That's when it makes the next present state. So that doesn't answer your question, but that does... I did need to put that in there, because if I don't have that in there, then I never get... It never makes this value right here. It never makes this present state. But...
Like, does it matter?
The only reason why is because this is... My indentation is not good here, because I think I'm missing... No, that's not it. I don't know. I know that I just copied this from him. So he just said he's making a clock of width 3 and then a clock of width 7. So it's probably just to pause a different amount of time between... I didn't think about it enough. I don't know. I will have to think about it some more.
Yeah.
So I don't have an answer for you on that one. But I did... You do have to have that in there. Okay. So now, let's see, there was a chat. Oh, you're welcome, Sage. I know you're long gone.